right? So we're talking now about damped harmonic motion rather than just simple harmonic motion. But I'm not just going to answer the questions in the exercise here. And what I'm interested in is what the book sort of omits, really. And I know it does it, for brevity, but I think it's important just to understand where the equation comes from. So I like to think of the equation for damped harmonic motion written like this, right? It's the same as what's in the book, and their letters and everything, but I've written it in this form, which is sort of a bit like force equals mass times acceleration. There's your mass times acceleration, and there's your force, right? And it is because, does this look a little bit like Hooke's law? Does this look a little bit like, tension is, whatever we add, like lambda times extension? Yeah, it does a little bit. And this here, then, this is our, our damping term, okay? So this is what we would have there. It's proportional to the velocity, and that is in common with much actual damping that goes on. So many physical systems, and I'm thinking of stuff like suspension on brakes, or the damping mechanism that's on a door would be proportional to the velocity. So that's what you've got. So that is sort of where that equation comes from, and then you can rearrange it to get what the book says, which is this. Okay, so there's our standard second order linear homogeneous differential equation. Okay, and how do you solve an equation like that? Well, you know how to do that. You get the auxiliary equation. Now, I reckon I derived the auxiliary equation a little bit when we were doing just simple harmonic motion, just because it was always the same. It was always just A cos omega t plus B sine omega t, but now it isn't. Now, I've started doing it here. This needs solving, so let's solve it. So we've got m, because that's what we're trying to find, equals, minus b plus or minus the square root of b squared minus 4ac all over 2a. Okay, now, I've written that atrocious, but there's obviously three situations here. What if this is positive? What if this is negative? What if this is naught? Because each of those three situations gives rise to something different. Positive, we've got real distinct roots. Negative, we've got complex conjugate roots. And zero, we've got repeated roots. So they lead to very different things and very different graphs, actually. So say it was positive. K squared minus 4 omega squared is greater than naught. Then we've got real distinct roots, and then we would have something that looks like a e to the invariably minus, but minus pt, I should use the alpha and beta, plus b e to the minus qt. What would that graph look like? It'd look like this. It's what we would call overdamping. Okay, so that's what that'd look like. That's overdamping. What if this was less than naught? So k squared minus 4 omega squared is less than naught. Then what's the situation then? That is what we would call underdamping. That is something like e to the minus pt times a cos qt plus b sine qt. And it looks like something like this. I'm not very good at drawing this, so I'm doing these little aids to help myself. Here we go. Okay, something like that, where anyway the oscillations die away. That's underdamping. Underdamping. And then the other situation is if k squared minus 4 omega squared equals naught. You'd have repeated roots, and you'd get this sort of situation, wouldn't you? A plus bt times e to the minus, keep using pt, and that sort of, it doesn't look dead different to this one, to be honest. It looks a bit like that, and we call that critical damping, as if like that's what you're aiming for if you're a damper. Critical damping. Right, okay, now I've shown you how to draw these graphs on Loom. So have a look at the Loom and see. This, to be honest, doesn't really help you in answering the questions in exercise 8C. It does really, but it's just a context to tell you where it comes from. Really, in exercise 8C, you just solve those differential equations and get the solutions. I'll post some solutions to those like in the next couple of days, and then I'll put some other solutions on Loom. But this is where it comes from. So just get solving the equations. Okay, nice one.